Number 10. The Collatz Conjecture. Pick a number, any number. Let's say you pick 6. It's even, so divide it by 2. You get 3. It's odd, so multiply by 3 and add 1. You get 10. Even, so divide by 2. You get 5. Odd, multiply by 3, add 1. You get 16. Then 8. Then 4. Then 2. Then 1. You always end up at 1. Always. Try it with 27. Try it with 1,000,000. Try it with any number your mind can conjure. You will always, without exception, spiral back down to 1. This is the Collatz Conjecture, and it is one of the most embarrassing open wounds in the history of human thought. It sounds like a children's game. It looks like a warm-up exercise in a middle school classroom. But this trivial little arithmetic trick has never been proven. Not once. Not ever. Mathematicians have verified it for every single number up to 2 to the 68th power. That is a number so large it dwarfs the count of atoms in the observable universe, and still, no proof exists that it works for all numbers. The legendary mathematician Paul Erdős once said of this problem, and we are paraphrasing here, that mathematics is simply not ready for such problems. Think about what that means. We have split the atom. We have sequenced the entire human genome. We have taught machines to write poetry and recognize faces. But we cannot prove what happens when you do simple arithmetic on a number and repeat it. The Collatz Conjecture sits there, smiling at you, childlike, innocent, bottomless. Number 9. The Riemann Hypothesis. Prime numbers are the atoms of mathematics. They are the indivisible building blocks from which every other number is constructed. 2, 3, 5, 7, 11, 13. You learned them in school. They feel familiar. They feel safe. But hidden inside the distribution of prime numbers is a secret so deep, so structurally important, that it underpins virtually the entire architecture of modern mathematics and cryptography. In 1859, a German mathematician named Bernhard Riemann noticed something. When he plotted a special mathematical function called the Riemann zeta function across the complex number plane, all of its non-trivial zeros, the points where the function hits 0, appeared to line up perfectly on a single straight vertical line. He called it the critical line. He suspected it was always true. He could not prove it. That suspicion became the Riemann hypothesis, and 166 years later, it remains unproven. This is not a quirky puzzle. This is the deepest unsolved problem in pure mathematics. Over 1,000 published mathematical theorems begin with the words, assuming the Riemann hypothesis is true. If it is ever proven false, entire mountains of mathematics collapse overnight. The Clay Mathematics Institute has placed a $1 million prize on its head. More terrifyingly, the distribution of prime numbers governs the encryption protecting your bank account, your messages, your identity online. We built the digital fortress of modern civilization on a foundation we have never actually verified. The primes know something. They are arranged according to a rule we can feel but cannot touch, and Riemann's ghost still waits for someone brave enough to prove it. Number 8. Imagine you are handed a completed jigsaw puzzle. Checking whether it is solved correctly takes you seconds. Every piece is in place. You can see it immediately. But if I scatter all the pieces across the floor and ask you to solve it from scratch, that takes hours, maybe days if the puzzle is large enough. This gap, the gap between checking an answer and finding an answer, is at the heart of the most consequential unsolved problem in computer science and mathematics. P is the class of problems a computer can solve quickly. NP is the class of problems where a computer can check a solution quickly, but may not be able to find one quickly. The question is devastatingly simple. Are these two classes secretly the same thing? If a computer can verify a solution fast, can it always find a solution just as fast? If the answer is yes, if P equals NP, the world as you know it ends overnight. Every encryption system on Earth shatters. Every password, every classified file, every secure transaction becomes instantly crackable. But more staggeringly, every problem in biology, logistics, medicine, and artificial intelligence that currently takes centuries of computation becomes solvable in seconds. Cancer treatments, climate models, drug discovery, all of it unlocked. If the answer is no, we live in a universe where some problems are fundamentally, irreversibly harder to solve than to check, where difficulty is baked into the fabric of reality itself. We do not know the answer, and the Clay Institute will give you $1 million if you find it. Number 7. The Goldbach Conjecture. Take any even number greater than 2, any one at all. 4, 28, 1,000. 10 million. Now try to break it into the sum of two prime numbers. 4 is 2 plus 2. Easy. 28, 11 plus 17. Sure. 1003 plus 997. No problem. It always works. Every single time. Go ahead and try to find an even number where it doesn't. You won't. Nobody ever has. This is the Goldbach Conjecture, first proposed in a letter written in 1742 by mathematician Christian Goldbach to the legendary Leonhard Euler. Euler, one of the most brilliant mathematical minds in human history, wrote back and called it an obvious truth. He could not prove it either. That was 283 years ago. Since then, it has been verified computationally for every even number up to 4 times 10 to the 18th power. That is 4 quintillion individual confirmations. The pattern holds without a single exception across a span of numbers so vast it is essentially incomprehensible. And yet, no proof, none, not even close. It is not that mathematicians haven't tried. Some of the greatest careers in number theory have been quietly consumed by this problem. The best result achieved so far is called Chin's theorem, which proved that every sufficiently large even number is the sum of a prime and a number with at most 2 prime factors. A near miss, a mathematical almost. The Goldbach conjecture stares back from the abyss, 4 quintillion pieces of evidence whispering that it's true. And mathematics, the one discipline built entirely on proof, still cannot say so. Number 6. The twin prime conjecture. Look at the prime numbers again. 3 and 5, 11 and 13, 17 and 19, 29 and 31, 41 and 43. Do you see it? Scattered throughout the infinite landscape of numbers are pairs of primes separated by exactly 2. They are called twin primes, and they appear again and again and again, no matter how far out into the number line you travel. The twin prime conjecture simply asks, do they go on forever? It sounds almost insultingly straightforward, but it has remained unproven since it was first formally posed in the 19th century. As numbers grow larger and primes become increasingly rare and isolated, does the universe keep producing these intimate pairs? Or does the last twin prime exist somewhere out in the numerical dark, beyond which primes drift apart forever, never to touch again? In 2013, a virtually unknown mathematician named Yitong Zhang, working in almost complete academic obscurity, stunned the mathematical world. He proved that there are infinitely many pairs of primes separated by a gap of at most 70 million. Not 2, but 70 million. It was still considered one of the greatest mathematical breakthroughs of the century. Subsequent work narrowed that gap down to 246. Still not 2. Think about that. Humanity's best collective effort, centuries of number theory, the combined processing power of modern computing, and the closest we have gotten is 246 when the answer we need is 2. The twin primes keep appearing, faithful, patient, daring us to prove they never stop. Number 5, the Navier-stokes existence problem. Right now, water is flowing through pipes beneath your feet. Blood is moving through the vessels in your body. Wind is curling around the corners of the building above your head. Fluid is in motion everywhere around you, every second of every day. And the equations we use to describe that motion, the Navier-stokes equations, work extraordinarily well. Engineers use them to build aircraft. Doctors use them to model heart disease. Meteorologists use them to forecast storms. But here is the mathematical horror buried underneath all of that practical success. We do not know if these equations actually work, not in the sense of practically working. They do that. We do not know if they are mathematically valid. We do not know if they always produce smooth, stable, continuous solutions, or whether under certain conditions they simply break. Whether the math spits out an infinite number, a singularity, a place where reality according to the equations just ruptures and ceases to make sense. This is not a minor technical footnote. If the equations break down, it means our mathematical description of fluid motion has a hidden catastrophic flaw. It means the foundations of fluid dynamics, aerodynamics, and climate modeling are built on ground that has never been certified as solid. The Clay Mathematics Institute lists this as one of the 7 Millennium Prize problems. $1 million to whoever can prove these equations always behave, or prove they don't. We use these equations every single day to build the world around us, and we have never once proven they are safe to use. Number 4, the Birch and swinnerton-dyer conjecture. This one starts innocuously, with a simple question that dates back to ancient Greece. Which numbers can be expressed as the ratio of 2 sides of a right triangle where all 3 sides are rational numbers? From that ancient seed grows one of the most labyrinthine and terrifying unsolved problems in all of modern mathematics, the Birch and swinnerton-dyer conjecture. At its core, it concerns a family of mathematical objects called elliptic curves. These are not the ellipses you drew in geometry class. They are smooth, looping curves defined by deceptively simple equations, and they carry within them a hidden algebraic universe of staggering complexity. The conjecture asks a fundamental question about these curves, specifically whether the number of rational points on an elliptic curve, points whose coordinates are fractions, is in some deep structural way connected to the behavior of an associated function called the L function. In plain language, it asks whether the shape of a certain mathematical object secretly encodes the solution set of an equation. Andrew Wiles, the mathematician who famously proved Fermat's last theorem after working on it in secret for 7 years, has called the Birch and swinnerton-dyer conjecture the most important unsolved problem in mathematics. It sits at the intersection of number theory, algebraic geometry, and complex analysis, 3 of the most powerful branches of mathematics, all pointing at the same locked door. Another $1 million Millennium Prize waits on the other side. The door has not moved. Number 3, the Hodge Conjecture. Somewhere in the history of mathematics, 2 great worlds grew up side by side. On one side, geometry, the study of shapes, surfaces, spaces, and the way they curve and fold through dimensions. On the other side, algebra, the study of equations, symbols, and abstract structures. For centuries, these 2 disciplines developed their own languages, their own tools, their own deep internal logic. Then, mathematicians began to suspect something extraordinary, that hidden beneath the surface, these 2 worlds were secretly the same, that every geometric shape carried an algebraic shadow, and every algebraic structure had a geometric body. The Hodge conjecture is the attempt to prove that this is true in a very specific, very deep, and very precise sense. It asks whether certain geometric structures called Hodge classes, which live in a high-dimensional abstract space, can always be built out of algebraic building blocks, called algebraic cycles. If you find that difficult to visualize, you are in excellent company. The problem exists in a mathematical dimension so abstract that even professional mathematicians describe working on it as navigating in total darkness. What makes it truly terrifying is the implication. If the Hodge conjecture is false, it means geometry and algebra are fundamentally alien to each other at their deepest levels. It means the 2 greatest languages mathematics has ever developed for describing reality are not, at their core, the same language. That the universe has 2 souls that do not speak to each other. Another Millennium Prize. Another sealed door. Another darkness that the greatest mathematical minds alive today cannot illuminate. Number 2, Gödel's incompleteness. In 1931, a 25-year-old Austrian mathematician named Kurt Gödel did something that should not have been possible. He proved that mathematics is broken, not in a practical sense, not in a way that stops bridges from standing or rockets from flying, but in a deep, foundational, almost metaphysical sense that mathematicians are still quietly horrified by nearly a century later. Gödel's incompleteness theorems state 2 things. First, in any consistent mathematical system powerful enough to describe basic arithmetic, there will always exist true statements that cannot be proven within that system. Always. No exceptions. No escape. Second, and more devastatingly, no such system can prove its own consistency. Mathematics cannot look in the mirror and confirm it is not lying to you. Read that again. There are mathematical truths that are true, that have always been true, that will always be true, and mathematics itself is constitutionally incapable of proving them. It means the edifice of mathematics, the most rigorous, most certain, most airtight discipline the human mind has ever constructed, is built on a foundation it can never fully verify. There is an endless supply of true things it cannot reach. Locked rooms in a house it built itself, with keys that cannot exist within the house. Gödel didn't just solve a problem. He proved that certain problems are permanently, structurally, cosmically unsolvable, not because we aren't smart enough, but because the language of mathematics itself has walls it cannot see past. The most certain thing humans have ever built contains truths it will never know it contains. Number 1, the nature of mathematical truth. And here we arrive at the bottom, the deepest, darkest, most destabilizing question of all. Not an unsolved equation, not a missing proof, something far worse. We do not know what mathematics is. Think about what you have just heard in this video. Prime numbers hiding infinite secrets, simple arithmetic loops with no provable end, geometric worlds that may or may not speak the same language as algebraic ones, a logical system that cannot confirm its own sanity. Every single one of these mysteries assumes that mathematics is real, that it is solid ground, that numbers exist somewhere in some meaningful sense. But do they? There are 2 terrifying possibilities. The first is that mathematics is discovered, that numbers, primes, geometric structures, and logical truths exist independently of the human mind, somewhere in a realm we cannot touch or see, and that mathematicians are essentially explorers mapping a territory that was always there. If this is true, then the unsolved problems in this video are not just hard. They are hard because they are real features of an infinite landscape that may be permanently beyond human reach. The second possibility is that mathematics is invented, that it is an extraordinarily sophisticated language the human brain created to describe patterns it perceives, that numbers don't exist outside the mind any more than the word tree exists outside of language. If that is true, then what are the unsolved problems? Are they gaps in reality, or are they gaps in our grammar? We have used mathematics to land rovers on Mars, to split the atom, to decode the human genome, to describe the birth of the universe itself. It works with a precision that borders on the supernatural. And yet, we cannot say with certainty what it is, where it comes from, or whether the truths it points to exist anywhere beyond the firing of neurons in a human skull. We built everything we know on this foundation: science, engineering, logic, civilization itself, and we have never once stopped to confirm that the foundation is real. You are standing on mathematics right now. You always have been. And somewhere beneath your feet, in a darkness that Gödel mapped but could not illuminate, the ground has no bottom.